Before we go over Lewis structure, I would like to explain to you what a structure is. Now, a structure tells us how different atoms are bonded in a compound. So in this example of H2O, we just wrote down two different ways. In both cases, the formula is H2O. In this case, two hydrogens are bonded to oxygen. In second case, you see that there are two hydrogens bonded to each other, and then one of those hydrogens is bonded to oxygen. So they are structurally different. In second example, you see that two hydrogens are bonded to oxygen, and on right hand side also we see there are two hydrogens bonded to oxygen. So structurally these two are identical, but they don't look the same. Now what is different in this case? Shape is different. One is a linear molecule, about 180-degree angle, and this is the bent molecule. This angle is less than 180 degree. So here we explain to you what structure is and what shape is. Now, and later on we're going to predict the shape, angles on the basis of what we call hybridization. In Chem 110, you already learned about Lewis structure of small molecules. In organic chemistry, we deal with large molecules, and in order to get Lewis structure of large molecules, would show you how we can quickly get Lewis structure of large molecules. Here we need to remember the following. In a neutral compound, carbon must have 4 bonds. Hydrogen must have 1 bond, oxygen must have 2 bonds, and 2 pairs of electrons. Also, we need to know that outer atoms must have 8 electrons. Outer or central atom must have 8 electrons except hydrogen, which can only have 1 bond or a pair of electrons. With those in mind, we can quickly write down Lewis structure of any compound. Say, for example, I want to write down Lewis structure for C2H4. So what I'm going to do first is going to write down 2 carbon. So let's write down C, that's 2 carbon. And then I'm going to distribute 4 hydrogens among these 2 carbon. And there'll be at least 1 bond. This is 1. This is the second one. This is the third one. And this is the fourth one. So that gives me C2H4. But the only problem is, if you look at this carbon, the carbon has 3 bonds, not 4 bonds. We already mentioned that carbon must have 4 bonds. But we don't have any additional hydrogen to make 4 bonds. So in that case, we'll draw a double bond. So this double bond would make 4 bonds for each carbon, this carbon as well as this carbon. So now this is the correct Lewis structure for C2H4. Now let's draw another Lewis structure in the same manner, CH3OH. So CH3OH, again, I'm going to write down first carbon and oxygen. Okay. So always I write down other than hydrogen. So you have carbon and oxygen, and I just wrote down 1 bond, and then remember carbon must have 4 bonds, and we have 3 hydrogens to give 4 bonds. So let's have those 3 hydrogens already bonded. So that makes CH3O. Then I need to add hydrogen. I cannot add any more hydrogen onto carbon because that would give too many bonds to carbon. So let's now add hydrogen here. And not only that, we also mentioned that oxygen must have 2 bonds. And in this case, oxygen does have 2 bonds. Now these are the 2 bonds. But in addition to that, there has to be 2 pairs of electrons. So I must have 1 pair. It doesn't matter how you draw those 2 pairs, as long as those 2 unshared electron pairs are on oxygen, then you'd be all right. So this gives you CH3OH molecule, and which is an alcohol. Now if it is a neutral nitrogen containing compound, you must assign 3 bonds and 1 pair of electrons. Again, that gives 8 electrons around nitrogen. Let's draw this compound. It's called methylamine, CH3NH2. So what I'm going to do first is carbon and nitrogen. I'm going to make that bond. And now I'm going to have 3 bonds for 3 hydrogens. And this gives 4 bonds around carbon because CH3N. Now I have 2 hydrogens, so it has to be bonded to nitrogen then. Now this gives 3 bonds to nitrogen. Now we said that 3 bonds and 1 pair of electron because that would give 8 electrons around nitrogen. So these are the 8 electrons around nitrogen. Bonded pair, there are 3 bonded pairs that would make 6 plus these 2, so that makes 8. So this is the Lewis structure for CH3NH2. So if you keep these rules in mind, you can write down Lewis structure of organic compound quite quickly and also accurately. Don't forget to assign pairs of electrons if it is nitrogen or oxygen. Next, we're going to talk about hybridization or mixing of orbitals. This mixing is done mathematically. That means if I combine one S, so this is S, which is spherical in shape, and say px orbital. Px would look like this. That would give me 2 sp hybrid orbitals, and each sp hybrid orbital would look like this. I just wrote down separately, but they'd be on each side of the central atom. This is the central atom, this is the central atom. So whenever you're mixing 2 orbitals, you do get 2 hybrid orbitals, which have similar properties. This is comparable to like you're adding flour to water and you get dough. Dough is neither water nor flour. Similarly, these hybrid orbitals are neither S nor px, but they have property which is uniform throughout. So these are 2 similar hybrid orbitals. Now these hybrid orbitals, sp, I'll talk in a minute, would be oriented like this. So pretty much that would determine the shape of the molecule which are bonded to these 2 hybrid orbitals. Now this would be again quick way of getting hybridization, bond angles, and shape of the compound. So keep in mind, if there are 2 pairs of electrons, we'd need sp hybridization. Now let me explain to you how this goes. S, px, py, pz, dz square, dx square minus y square. Then you have dyz, dxz, and all those 5 d orbitals. So we don't need this for most organic compounds. So that's why I'm not writing down other d orbitals after dx square minus y square. For 2 pairs of electrons on the central atom, I'm going to combine these 2 orbitals. So always you start with S. Why I need to combine 2 orbitals? For each pair of electrons, you need 1 hybrid orbital. So for 2 pairs of electrons, you need to get 2 hybrid orbitals. And the rule is, if you mix 2 orbitals, you end up with 2 hybrid orbitals. So sp, I'm mixing S and P, px, that would give me 2 hybrid orbitals. And what we are saying here is, if there are 2 pairs of electrons, that would give me 180 degree hybrid orbitals. Now, we can quite quickly understand that why is 180 degree. Let's assume that this is the central atom. And I'm putting 1 pair of electron here and another pair of electron here. But knowing the fact that electrons repel each other, this is not going to be very stable. They try to stay away farthest from each other. So that means the best configuration would be like this, 180 degree from each other. So sp has two hybrid orbitals and they would be 180 degree from each other. Similarly, for three pairs of electrons, again I'm going to combine in such a way that I obtain three hybrid orbitals, because we have now three pairs of electrons. So which orbitals we are going to combine? S, px, and py. By combining these three orbitals, I'm going to get sp hybrid orbitals. So sp really means that I combine s and two p orbitals, which is px and py, just to get three hybrid orbitals. And three hybrid orbitals would be at 120 degree apart from each other. Again, you can understand it very well. Let me show you underneath. Say I have three pairs of electrons. This is my central atom. This is one pair. This is the two pair. Let's assume that this is the three pair. Again, knowing the fact they repel each other, so this is not be the best geometry because they try to be away from each other. So the best shape would be, you can quickly figure out that it would be like this. When they're farthest from each other and about at 120 degree from each other. So this is going to be the best orientation or shape of these hybrid orbitals with three pairs of electrons. So this already determines the angle, and that's why we say for three pairs of electrons, angle would be 120 degree. And keep in mind, for each pair you need one hybrid orbital, and that's why we needed sp2 hybridization for three pairs of electrons. So this is going to be one sp2, this is going to be the other sp2, this is going to be the other sp2. And keep in mind, these hybrid orbitals pretty much work like a hand. Each can hold on to one element. So that's how bonding takes place. For four pairs of electrons on the central atom, there are lots of examples in organic compounds of four pairs of electrons. With four pairs of electrons, hybridization would be sp3. Why? Because for each pair I need one hybrid orbital. So I need to combine four orbitals. So I'm going to combine s, px, py, and pz. And that makes it sp3. So sp3 would have four pairs of electrons, and there'd be four identical orbitals, and they would look like the following. If this is my central atom, 1, 2, 3, 4. Keep in mind this is three-dimensional, so it's hard to draw on two-dimensional surface, but this is how I'm trying to give you the appearance of this molecule. This is called tetrahedral. I strongly suggest that you have molecular models so that you can build these structures from the beginning, so you get a good feel for how they would look like. These angles are not 120 degree or 180 degree, or this 109.5 degree. 109.5 degree. So with four pairs of electrons, angles are going to be 109.5 degree. Something else you need to know is double or triple bonds would be counted as a single bond or one pair of electron for determining hybridization and shape of molecule. Now if I give you examples, you'd quickly understand that in which cases you'd expect sp3 hybridization. Think about H2O. So I can write down H2O like this now without knowing anything about the shape. Remember, I have oxygen with two bonds, and oxygen must have two pairs of unshared electrons. Now I have altogether 8 electrons around oxygen. That would be the first thing to know before you get hybridization. Now for hybridization, I need to know how many total pairs of electrons I have around the central atom. My central atom is oxygen, so now I have 4 pairs of electrons. As soon as you find that there are 4 pairs of electrons, you must get 4 hybrid orbitals. That means you need to combine these 4 orbitals, s, px, py, pz. So that would give me sp3 hybridization And remember, sp3 hybridization sets the angle at 109.5. That means it's going to look like this. Water would look like this with two hydrogen bonded here. And other two hybrid orbitals have unshared electron pairs. Those are these unshared electron pairs. So this angle would be, in this case, we'd say close to 109.5. So this angle is close to 109.5. But the fact is, whenever you have unshared pairs of electrons, they squeeze the angle to a smaller value. That's almost always is the case. Unshared electron pairs, they squeeze the angle of bonded pair because of the repulsion like this, which is quite significant. And that's why we said that this angle is not quite 109.5, but slightly less than 109.5 degree. If I didn't have any of these lone shared of unshared pair of electrons, then angle would be 109.5, like in case of methane, CH4. Let's draw methane. Here I have 4 pairs of electrons around carbon. So again, my hybridization is sp3. They're all bonded. There's no unshared electron pair. So since it's sp3, sp3 goes with 109.5 degree. So each of these angle is going to be 109.5 degree. And since there is no unshared, obviously, they are going to remain as at 109.5 degree. Now we are going to draw quickly some of these inorganic compounds so that you would know the difference in drawing inorganic compound as well as organic compound, which we just discussed. Now in inorganic compound, we just go by plus and minus sign on each element. Like sodium, that belongs to group 1A. If you look at periodic table, the first column is group 1A. Group 1A elements would have plus 1, 2A elements would have plus 2, 3A would have plus 3. Beyond 4, you subtract group number from 8. So that gives minus 3 for 5A, minus 2 for 6A, minus 1 for 7A. We leave out group 4 because it can have a number of more than one oxidation numbers. These are called oxidation numbers, these pluses and minuses. Let's explain to you how we come up with this formula in case of inorganic compounds. First, we figure out that calcium is from group 2A, so calcium must have plus 2. So calcium is plus 2 or 2 plus. And Cl must have minus 1. So before you write down formula, forget about these pluses and minuses. So this 2 goes down here, 1 goes here. So that gives me calcium 1 Cl2. So we don't write down 1, so we just write down Ca Cl2. So that's the formula of calcium chloride, which is an inorganic compound. So from here you understand that how we come up with inorganic compounds, which you mostly learned in Chem 110 or more other basic chemistry courses. And today you also learn how to draw structure for organic compounds and how to determine shape based on hybridization. Here you see the actual hybridization based on the shapes of different orbitals. This is S orbitals is spherical, this is S, this is px having 2 lobes on 2 sides. sp hybrid, this is basically 2 hybrid orbitals. One is this one, the other one is this one. So they act like hands to grab other element. Now this is showing you actual how sp3 would look like. So S, Px, Py, and Pz combined together. So that's how we got 4 hybrid orbitals. And each hybrid orbital would act like a hand to grab other atoms. Just a few seconds ago, I mentioned about hybridization and molecular shape for double and triple bonded compounds. When you have double or triple bonded compounds, consider double or triple bond as a single bond. So in this particular case, you see that this carbon, let's focus on that carbon, had the triple bond on one side, this is triple bond on one side, and 1 bond on the other side. So we'd be counting triple bond as 1 bond or 1 pair of electron, and the other bond as another pair. So basically we'd count that this carbon has 2 pairs of electrons. Remember, for 2 pairs you'd need sp hybridization. Remember the hybridization as px, py, pz, and then you have all these d orbitals. Now for 2 pairs I need this sp, so I'd say it must have sp hybridization. At this point you ought to know what angle goes with sp hybridization. It is 180 degree, so you need to know. Now let's try another case. On this side, of course, this carbon case is similar to this carbon. So here also you have triple bond, would be counted as 1 bond or 1 pair of electron. This is the other pair. So you'd be counting as there are 2 pairs. So again, this must also have sp hybridization, and angle would be 180 degree. So let's draw the right structure. So you'd have something like this. So this compound not only gives the right Lewis structure, it also gives the right shape. And these angles are 180 degree. So we quickly figured out that based on hybridization. Now let's try to do the same kind of example here. In this case I have carbon. Carbon has 4 bonds. That means 4 pairs of electrons. 4 pairs of electrons means I must combine these 4 orbitals, spx, py, pz. So that would mean sp3 hybridization, and we know sp3 hybridization goes with 109.5 degree. So that means this angle number 3 is 109.5. Let's try to figure out hybridization for oxygen. Again, altogether we have 4 pairs of electrons. 2 pairs, these 2 pairs are we call lone share or unshared pair of electrons. Lone pairs of electrons are unshared electron pairs, plus 2 bonded electron pairs. So that's 4 pairs. That would also give sp3 hybridization. So this oxygen has sp3 hybridization, and remember, sp3 hybridization goes with 109.5 degree. And so this angle would be 109.5 degree, but keep in mind, to be more accurate, since we have 2 unshared electron pairs, unshared pairs of electrons would squeeze the angle to smaller value. So we say slightly smaller. Would be slightly smaller. Sorry that my writing doesn't look too good. So this would be slightly smaller than 109.5 degree because of these unshared electron pairs. Now let's try to get hybridization and shape around this carbon. Now we have a double bond here, so it would be counted as a single bond or 1 pair of electron. This would be counted as the second pair. This is the third pair. So we have 3 pairs, so I must combine these 3 hybrid orbitals, sp, x, py, pz. Remember, for each electron pair you need 1 hybrid orbital. So you need sp2 hybridization for this. And remember the angle that goes with sp2, which will be 120 degree. So this is how you should be able to correlate hybridization and angle, and that would automatically provide you the right shape of the molecule. Now here we're showing you different type of hybrid orbitals again. sp, you're seeing sp hybrid orbital. This is one of them. This is the other one. This is both sp orbitals on 2 sides of the central atom. This is showing you sp3 hybrid orbitals. These are all taken from the book. This is s, this is px, py. So that gives you sp2. Here we are seeing sp3 hybridization. This is the s, and you see px, py, pz, and this gives you sp3 hybrid orbitals. And there'll be 4 in number because you combine 4 orbitals. In this slide, you're seeing bonding in a compound, which is CH2CH2 or C2H4. So basically, you're looking at this compound, CH2 double bond CH4. H2. What you are looking at are called sigma bonds. Sigma bonds are formed by head-on overlap of orbitals, like sp2 of this carbon is overlapping with sp2 of this carbon. Electron pairs are like glue. It would be sitting in between. So as if they're shaking hands, they get a good grip. Similarly, sp2 of this carbon overlaps with 1s of hydrogen. sp2 again, same thing, sp2 of same carbon. This is sp2 of the same carbon is overlapping with hydrogen on this end. And each of these bonds are formed by head-on overlap, and these are sigma bonds. So here you can see there are three altogether. This is one sigma bond, this is the second sigma bond, this is the third, fourth, fifth sigma bonds. Now these are pz orbitals. Even though in this picture they're shown far apart from each other, truly they're pretty close to each other and they're just touching each other sideways. So this is called pi bond. The pi bonds are formed by sideways or lateral overlap of orbital, in this case 2pz orbital. Now you can think about, in one case there is head-on overlap, which is sigma bond. Another case, as a bond is formed by sideways overlap, so the overlap is not very significant. So you can then predict which bond is going to be weaker and which bond is going to be stronger. Obviously, that sigma bonds, because they're formed by head-on overlap, will be a stronger bond than pi bonds, where there is not effective, there is not an effective overlap. In this slide, we are showing you pi bond. As I said, that these two hybrid orbitals are not that far. They're closer to each other, so there's a slight overlap along the side. And that gives rise to this kind of hybrid orbitals. And electrons can move around on the top or on the bottom. So that gives you pi orbital. Now, so keep in mind, when there's a double bond like this, don't forget, even though in Lewis structure we don't distinguish these double bonds, but truly they're not same kind of bond. One of these bonds is a sigma bond, which is formed by head-on overlap, which is a strong bond. The other one would be a pi bond, like this, where there's a sideways overlap. So in organic reactions, quite often you'd find that it's the pi bond that would break down rather quite promptly, because of this weaker bond. It doesn't need much energy to break down, and the other bond would remain intact. So keep that in mind when you see a double bond. Don't think that both these bonds are identical. Similarly, in case of a triple bonded compound like this, remember it would have sp hybridization, and one of these is sigma bond, the other two are pi bonds, or weaker bonds.